My name is Sarang Sharma and we are from group number 10. We are here to present our works on navigating the microservices terrain, a comprehensive literature survey. These are our group members. We would be analyzing several of the concepts, several challenges, several issues concerning microservices. But starting with what are microservices? Microservices refers to small independent services which work together to form an application. Each microservice is responsible for performing a specific subset of applications. This differs from the traditional monolithic architecture wherein the entire application is encapsulated within a single binary. So microservices provides us the advantages of modularity and reusability. A schematic showing the differences between monolithic and microservice architectures. We aim to find the specific design challenges and the performance issues that current microservice architecture experiences and the solutions suggested in the current literature. We also want to analyze whether these solutions are good enough or do they have some limitations. Starting with the primary concerns of microservices, security. The sheer volume of services increases the attack surface. Independent services increase the vulnerability risk. Every microservice communicates with one another using APIs which can be violated or which can be exploited. We also require secure communication channel, authentication, authorization, which is difficult across distributed systems. So the paper Microservices Made Attack Resilient using unsupervised service fissioning aims to make them resilient to application layer denial of service attacks and reduce latency in case of attacks. So it uses the CPU utilization and memory utilization data along with a first order autoregressive model for detecting anomaly. Once an anomaly is detected, it utilizes the service fissioning approach, that means quarantine the affected node, reserve a set of replicas and redirect the request to this particular quarantine node to the replicas. The results show that the latency dropped significantly with the new model when an autoregressive model has been used than the baselines. However, despite the better performance, there are some limitations. This model primarily focuses on application layer attacks and it may not address other security threats. Unsupervised service fissioning has not been extensively tested, so we don't know whether it can be used in a real life scenario or not. First order autoregressive model might not be able to capture the intricacies of the attack, and the scalability is a very major issue. Another paper enhancing microservices security with a token-based access control method proposes token-driven access control methods for authorization and authentication. The next major issues that microservices fail is fault tolerance. Due to their distributed nature, they have more point of failures than the monolithic applications. Coordinating, managing interactions, diagnosing the issues is a major challenge in this case. The potential for cascading failures also create problems. And the major task is to maintain consistency and durability in case of failures. So most of the fault tolerant algorithms either study the fault detection algorithms or the fault tolerance one. Dynamic microservices to create scalable and fault tolerant architectures proposes a dynamic distribution of tasks between clients to provide redundancy and continuous monitoring and handling of client failures to ensure the system remains stable. Another paper, detection of faults in microservices using Petri nets, uses a Petri net model, a model which is generally used to describe distributed systems, a collection of states and transition between states. These Petri net models are used for several failure identifications such as incorrect sequences of asynchronous operations, missing information, long response time, timeout, service failures. And once these failures have been detected, the fault tolerant algorithms or the algorithms which will provide stability can be applied.
Everyone, I am Pranav Mehrotra, and after discussing the security aspects of microservices, we will now discuss the network aspects and its challenges in the microservices environment. The microservices communicate with each other with the help of RPCs or remote procedure calls. There are mainly two methods of communication, synchronous and asynchronous. The current state of the art method used in the RPC framework is the gRPC, which is developed by the Google. And it is a high performance RPC framework, but it is quite complex in comparison to the REST API. And also the protocol buffer based serialization used by the gRPC has a lot of intricacies, and the HTTP version 2 based communication can be quite challenging for the developers. So there is a definite need for optimization. Since we know that microservices generate high volumes of data and small RPC requests, therefore to optimize the quality of service, we need to minimize the latency and also reduce the stress on the networking stacks. But the current RPC frameworks do not suit the modern day microservices workloads. Therefore, we need to improve the performance, scalability, and the reliability of the microservice framework. The main criteria used for the evaluation of two microservices is the latencies, and mainly two types of latencies are considered, that are communication latency and tail latency. The communication latency measures the average RTT time between a request and response pair, and whereas the tail latency considers the worst case scenario and in the microservices architecture. So the challenges in optimizing communication latencies include the cross-region network RTT, which is heavily dependent on the current network delays and the routing protocols and the network congestion, and this all impacts the RPC latency. And there is also the delay of local queuing used in the system, which leads to a risk of overloading of the system and also increases the error rates of the system. Also, the network RTT affects the server utilization ratio, where a server can be waiting for the packets to come for a long time, and which decreases the server utilization. One of the solutions is the service router, which is an application-based proprietary solution by Meta. They follow a latency-focused approach where they route the request to local servers until the queuing delay threshold is reached, and also they also focus on optimizing the server utilization and also predicting the latency of the system. They use locality rings and latency monitoring service and a centralized monitoring service so as to monitor the current network state and adapt the system to the current workload of the network. They also introduce a new technique called RPC connection reuse, where they randomly sample two servers from a stable subset of servers and maintain a connection reuse between those servers, and thereby reducing the overhead of establishing new connections for every RPC request. All these optimization results in 25 to 50% effectiveness, and also the service routers library reduces the hardware costs by 99%, and because they do not go through the extra hop of the proxy and they directly jump from clients to the servers. But there are certain limitations to the service router, and these include that the service writer for a new deployment can be very much challenging, and also the overhead of the service writer and service proxy for a tail latency can be large, because they only optimize the communication latency and do not focus on the tail latency. And also the current evaluation methods used by the authors may not fully represent the real world scenarios. Next, we come to the challenges of the tail latency optimization. The main challenge is the microsecond scale challenge, where the scheduling policies used by the microservice environment for the processes can be microsecond overhead, and also the inter-thread communications. And there is one more major complexity, where the number of configurable parameters in a system can be large, and they are very much correlated to each other. So finding an optimal configuration for your system is a challenging task. The two solutions proposed are, the first one tries to find a optimal configuration for the microservice system. It uses a Bayesian optimization approach, particle swarm optimization, and a dimensionality decreasing search, and it compares all the three approaches and evaluates them to find the optimal approach. The second one proposes a new model called Concord, which has a dedicated dispatcher thread and multiple worker threads. The design is to approximate the optimal scheduling policies of the processes rather than actually implementing the original policies, which allows the author to reduce the overhead by a lot while still maintaining the optimal scheduling. And they also wanted to strike a balance between the tail latency and the throughput of the system. The benefits of the Concord can be seen by the demonstration that has been given by the authors on the throughput benefits that are received by the Concord's performance, and also the new techniques introduced by the author are very much optimized according to the existing scheduling policies. But there are certain limitations, the biggest one being that the authors used a custom compiled language, where the application source code must be written in that compiled language, which introduces a huge code sharing requirement for the public cloud providers. And also the single dispatcher system, the current prototype is actually limited to a single dispatcher system, which can be a huge scalability bottleneck, because the service time will decrease over the time and the number of CPUs increases over the time. Thank you. That is all from my side.
Hello everyone, my name is Pranayati, and after having discussed network challenges related to microservice design, I'm now going to discuss two key aspects. One is service decomposition and second benchmarking for microservices. So let's get started with service decomposition. Basically deals with how to decompose a monolithic service or application into smaller and independently deployable services, and it enhances the scalability, flexibility, and maintainability of the microservice system. Now, there are two main characteristics that define the extent of service decomposition adopted in the design of a microservice. First is cohesivity of services. A set of cohesive services exhibit a specific purpose with minimal dependence on external components. There are several factors that determine the extent of cohesion of services, such as functional and temporal cohesion. Functional cohesion means that the service should encapsulate similar functionalities together, and temporal cohesion means that the service should handle operations with similar temporal characteristics together. The second aspect is coupling of services, which refers to the degree of interdependence between services. Tightly coupled services have strong dependencies, while loosely coupled services have minimal dependency. Now, let's discuss the two the different design service decomposition paradigms that are generally practiced. First is domain-driven design, second is functional decomposition, and third is data flow-driven decomposition. The details of these are given in the report for the project. Next, let's discuss a recent work, Blueprint, a toolkit for highly reconfigurable microservices, which proposes a generic microservice development toolchain for development of microservices that are loosely coupled, and it employs the design principles from service decomposition. The authors aim to address the ability to rapidly develop and reconfigure applications and to iteratively configure, build, and deploy new variants of an application that alter or improve its design. Thus, their framework facilitates effective and faster microservice experimentation by researchers in a systematic manner. The authors propose a three-phase decoupling for the design of microservice application. They propose that any microservice application can be decomposed as follows. First, its application level workflow. Second, its underlying scaffolding components such as replication and auto-scaling framework, etc. Third, the concrete instantiations of each of those components and their configuration. Now let's look at the detailed design framework. So they follow two major principles in the design. First is separation of concerns. Authors observe that an application's workflow, scaffolding, and the instantiations, so all these three components are actually conceptually orthogonal and independent in most of the real-world systems, and thus they should be separable when specifying the application architecture. The second thing that they follow is compile time integration. So this blueprint framework combines the workflow, scaffolding, and instantiations not at the time of development code, compile time, thus avoiding time coupling. And the authors have integrated a compiler with Blueprint, which is responsible for later generating the code that instantiates, configures, and addresses services at the application process and container levels. Let's look at the implementation of Blueprint. So any application that is developed using the Blueprint framework has two key abstractions. First is the workflow specification. The second is the wiring specification. The workflow specification is the implementation of the Acts workflow, and the developers can declare an interface with type methods and provide the implementation. Currently, it supports Go language. The wiring specification deals with scaffolding and instantiations, which are implemented as compiler plugins. They are declared using a strongly typed domain-specific language with C-style macro support. Now, the next key component in the implementation is intermediate representation. It's a representation of any blueprint microservice generated by the compiler. The compiler takes the input, the application's workflow and wiring, and generates the intermediate representation. This is basically a well-structured graph that represents the concrete topology as well as hierarchy of all the components along with the interaction and interdependence. The blueprint compiler is of two phases. The first, the compiler processes the wiring and workflow specifications to instantiate the intermediate representation graph, and then using the IR graph, it invokes compiler passes and scaffolding specific plugins for each of its individual nodes to generate runnable artifacts. The use cases of Blueprint are first, mutating applications, second, reproducing emergent phenomena, and third, prototyping and evaluating improvements. Next, let's get to benchmarking of microservices, which involves systematically evaluating the performance, scalability, and reliability of any system by comparing it against established standards. This entails measuring various metrics such as response time, fault tolerance, resource and CPU utilization, etc. The importance of benchmarking is, first, it helps identify bottlenecks and key areas for optimization. Second, it ensures that service level agreements are not violated and helps validating functional and non-functional requirements that the users expect from the application. It also helps to understand system behavior and emergent phenomena under varying loads. The challenges in benchmarking, in design of benchmarking systems are there are complex interdependencies between microservices and dynamic nature of containerization. Second, there is lack of standardized metrics. Now let's discuss two specific benchmarking tools. First is MuSuit and second is Death Star Bench. The MuSuit aims to characterize the influence of OS and networks-based effects on microservices and has four service components: image similarity search, a protocol routing for key value stores, set algebra posting list, and a recommender system. The key design components of MuSuit are thread pool architecture, polling, asynchronous communication, and dispatch-based processing. Now let's discuss the Star Bench. This focuses specifically on large-scale applications with several unique microservices and helps to allow studying effects that only emerge at large scale in real-world systems, such as network congestion and cascading QoS violation. This includes diverse apps which resemble real-world applications such as social network, e-commerce sites, banking system, etc. The key design components of this star bench are representativeness, end-to-end operation, heterogeneity, and reconfigurability. That was all from my side. Thank you.
Hello, my name is Anand Kumar Parikh, and I will be talking about the topics load balancing and resource allocation in microservices. The basic idea of load balancing is to distribute user requests, that is north-south traffic, among multiple servers, each of which individually performs some computation and or operates on some resource. Microservices involving hundreds of submodules require intercommunication amongst these modules, and hence also need internal load balancing of east-west traffic. First, let's discuss some of the design challenges that arise while designing a load balancer for microservice applications. Load balancers are the first point of contact of users with any system. All requests go through load balancers for mapping to a particular server replica. So the operation of a load balancer directly affects the latency and response times faced by users. Since all servers are allocated tasks by the load balancer, the CPU utilization, memory and disk requirements, and networking overhead at servers is also decided indirectly by the load balancer. In microservice architectures, servers might be interdependent, so load at a given server also affects the load at other servers dependent on it. It is also the load balancer's responsibility to ensure fault-tolerant functioning in spite of unpredictable traffic, congestion in the network, and small or large system failures happening continuously at different points. Microservices, unlike monoliths, are updated multiple times a day, so the load balancer must adapt to such dynamic configuration changes automatically without any manual intervention. Some additional tasks that the load balancers are generally given is service discovery and logging of performance metrics at different servers and preventing malicious unauthorized access to the system, etc., etc. So load balancing is more than just distribution of traffic, especially in microservices. There are many combinations of possibilities that one must consider to design efficient, scalable, and secure load balancers. The load balancing algorithm defines what technique to apply while mapping client requests to servers. However, in complex systems, defining the load itself is a challenging problem and can comprise a customized combo of CPU time, memory util, or number of active requests being served. Interestingly enough, the load balancer itself may be a decentralized service running multiple instances jointly, acting as a single load balancer, which allows for better horizontal scaling at the expense of more complicated communication and consistency amongst these replicas or these instances. Now, we discuss a specific load balancing technique, host-enabled eBPF-based load balancing scheme, or in short, HEALS, which combines the best of centralized and decentralized techniques, providing a transport layer or L4 load balancer. HEALS uses a centralized load balancer receiving requests from clients to be mapped to a group of backend servers. HEALS utilizes a customized TCP option called HEALS in TCP packets for establishing the TCP three-way handshake. The client sets HEALS equal to client IP or CIP while sending the SYN packet to the load balancer's virtual IP or VIP. The load balancer rewrites the source IP from CIP to VIP while maintaining HEALS equal to CIP before forwarding to a chosen destination server DIP. Now, upon receiving the packet SYN, the SYN plus ACK packet in the SYN plus ACK packet, the server can set the destination to CIP so as to directly connect with the client and set the source as VIP. So as the client believes that the packet comes from the load balancer and sends its own IP, that is the destination IP or DIP, as HEALS equal to DIP. At the client side, upon receiving the option HEALS, receiving the option HEALS provides the destination server. This scheme is highly useful in microservices since it does not require any kernel modifications or insertion of kernel modules at the client, load balancer, or server side at all. The source and destination IPs are set appropriately at every stage to use the regular TCP protocol. In addition, the load balancer comes into play only once while establishing the TCP handshake, and further communications are directly between server and client, thereby decentralizing all other requests. It is an architecture agnostic general solution, making it deployable to public cloud systems and compatible with proprietary load balancers and microservices. Experimental results show that HEALS adds no data transfer latency and has a very small throughput overhead of only nearly 3%. Now, we explore the aspect of resource allocation, consistency, and concurrency in microservices. The broad idea is that for ensuring higher availability and to allow concurrent access to a resource in a distributed environment, a particular resource, say a file, is replicated across servers. However, these replicas must now be coherent by guaranteeing some degree of consistency. The model that is used widely in most databases is ACID, which says that all transactions must ensure atomicity, consistency, isolation, and durability. It prefers safety over liveness. Distributed transactions achieve ACID properties for resources in a distributed environment by implementing the famous two-phase commit protocol, or 2PC. In 2PC, basically a leader synchronizes access to a replicated database for all the follower nodes. In phase 1, the leader sends requests to all followers to remember a transaction, but not immediately execute it. Upon receiving sufficient acknowledgements at the end of phase 1, the leader initiates phase 2, where it itself commits the transaction and commands the followers to commit it. However, this is not very popular in distributed applications, especially microservices, because it is a blocking protocol requiring a database to be locked for write operations. It can take very long time to terminate and possibly even deadlock in cases of high load, leaving the system useless. Also, the ACID properties are generally not required in many distributed applications. So contemporary literature refers to a base model, saying that the resource must be always basically available, that is always available, and the state is stopped, meaning it is subject to change and not immediately final. The model provides eventual consistency, which is the weakest form of consistency, which means that the state at different replicas can be inconsistent temporarily, but eventually all replicas will converge to the same state. This model clearly prefers liveness over safety. The saga pattern enforces base conditions. A saga is simply a sequence of events that must occur at distributed replicas. It is originated by some initial user request. After computation locally at the first service, that is, let's say service A, the service A emits a message in response to which the second service, service B, starts its local computation and so on. If all the services in the saga execute correctly, the transaction has ended successfully. However, if at any stage any intermediate service fails to perform a computation, for example, service C, it sends a rollback message to the previous service, which rolls back its own local computation and recursively emits a rollback message to its predecessor, and so on and so forth, until all instances have rolled back and the transaction has failed. In both cases, we can see how eventual consistency is guaranteed. The benefits of this model is that results are achieved faster without any possibility of deadlocks. However, there are some drawbacks that the end users may temporarily see conflicting results. Also, it increases the complexity of programming since the underlying model has weaker safety guarantees. Thank you.
So, moving on to monitoring proprietary microservices. Now, the broad idea is that proprietary microservice applications like Amazon AWS, Azure, Google Cloud have been highly influential and used in a lot of critical applications, but they have been pretty opaque with respect to their inner functioning. So, in case such services need to be used for critical applications, we need to analyze these microservices in terms of relevant system-wide performance metrics. However, the widely available open source benchmarks used for this purpose are not able to fully capture the complexity of such cloud applications. Coming to the challenges, there are three broad approaches to study proprietary distributed applications. The first is to actually use the benchmarks used by the cloud providers. However, even though this approach would have been the most appropriate choice, companies usually do not provide the benchmarks that they use to test out these cloud services on their own systems. The second thing is to use a technique called like trace replay. However, trying to monitor cloud applications using trace replay means that the trace obtained is dependent on the system configuration during trace collection. Hence, it's not generalizable. Another approach, which is quite promising, is to create a faithful clone of the original application, which can be tested out separately. However, prior work in this regard has only been done on CPU-centric single-tier user-level applications. To this end, the authors of the paper Application Cloning for Distributed Microservices Using Ditto propose a new approach called Ditto to clone closed-source proprietary cloud services. These applications can either be monolithic or they can be microservices. They also ensure that the created application clone is faithful to the original application in terms of the measurable system metrics. Now, what's the design approach? Ditto follows a four-stage approach. The first is microservices topology, where Ditto learns RPC dependency graph between individual microservices using distributed tracing. It uses that to then create APIs between these individual microservices. The second approach is to create an application skeleton. For this, Ditto analyzes the thread and the network model, whether it's synchronous or asynchronous and all, and uses that to build a skeleton of each service. As you can see, there are socket-based functions like poll, accept, and wait for this very purpose. Now, coming to the application body, Ditto creates an application body by creating clones of the assembly instructions, kernel level assembly instructions, which kind of are able to mimic the observed patterns in branch behavior, data memory access pattern, and other system-wide metrics. Finally, Ditto, using the differences between the cloned and the original application, it uses that to fine-tune the clone generator. Now, who benefits from this? Hardware vendors benefit from this because they can use that to obtain synthetic versions of their own closed source applications for hardware testing. Cloud providers also benefit because they don't need to disclose their source code to hardware vendors to allow them to test out their services. And finally, researchers also benefit from this because they can use these synthetic clones for research without having to get access to these production services. Finally, this is our conclusion. The primary focus of our work on microservices was on the following aspects as shown here. Thank you.